So you probably noticed recently that we've been able to tell if a reaction is spontaneous or non-spontaneous just by calculating the cell potential. And by seeing if it's a positive or a negative sign, we could say if it's spontaneous or non-spontaneous. So in this section, we're going to relate what we've been learning about cell potential back to what we learned about Gibbs free energy, or the Gibbs free energy change, delta G, from our previous chapter on spontaneity and thermodynamics. So we have an equation that relates the free energy change and the cell potential. And that says that delta G is equal to negative NFE. And we'll go through what each of those terms mean. So little n is the symbol we use to represent the number of moles. And in this equation, it represents the number of moles of electrons transferred. F, capital F, is called the Faraday constant, and that is the electric charge on 1 mole of electrons. So it's just a constant value, nothing you have to memorize. It'll be on your equation sheet. It's 96,500 coulombs per mole of electrons that are transferred. And then E naught is that standard cell potential, and that will be in volts. And then delta G, as we saw before, is the Gibbs free energy, and so that's in units of joules, or sometimes you'll see that in units of kilojoules, but it's an energy. So now we can calculate Gibbs free energy just by knowing the cell potential for a reaction, or vice versa. If we knew the Gibbs free energy, we could find the standard cell potential. So just a reminder, a negative delta G corresponded to a spontaneous reaction, and a positive E, or a positive E cell, was a spontaneous reaction. Let's try an example where we calculate the delta G for a given reaction by using the cell potential. So calculate the standard free energy change. So when we read that, we want to immediately think delta G for the following reaction at 25 degrees Celsius. And notice we're at 25 degrees C because we are given a standard cell potential, which is why that naught symbol is written after the E in the first place. So that means 298 Kelvin and 1 atmosphere pressure, 1 molar for our solutes, etc. So when we look at our reaction, we have our zinc being oxidized and we have our copper being reduced. So our reduction half reaction is going to be our copper 2+ gaining 2 electrons to become elemental copper, and our oxidation half reaction is zinc becoming zinc 2+, losing 2 electrons. So when we look at the individual half reactions, in this example, the electrons that are gained in the reduction half reaction are exactly equal to the electrons lost in the oxidation half reaction. They're both 2. So these two are essentially the same, so N is equal to 2 moles of electrons. Now that isn't always the case, and sometimes you have to actually balance the half reactions to find out how many moles of electrons are transferred. You might remember doing that when you learned about redox, balancing redox reactions in Gen Chem 1. But since they both were 2, that means 2 electrons were transferred in this case. So N is equal to 2. And sometimes you might actually even have to calculate the E cell, just as we were doing in example problems in the previous lecture. But in this problem, the E cell was given to us for this reaction, a positive 1.10 volts. So this reaction should be spontaneous. We have a positive E cell. That kind of tells us, hey, we should expect a negative delta G when all is said and done. It's good to kind of think about what you should expect before you even get that. So now we take our equation and we're going to essentially plug our information into it. We had our new equation said the delta G was equal to negative N F and then E cell, where F was that Faraday constant, and so that's going to be equal to negative 2 moles of electrons that are transferred in this reaction times Faraday constant, which is 96,500 coulombs per mole of electrons that are transferred, so you can see where that will cancel. And then we're going to multiply by our E cell. Now notice our E cell is written in volts, so it looks like your units won't cancel. But just a reminder that 1 volt is actually equal to 1 joule per coulomb. So anytime we see volts, we could cross that off and write joules per coulomb. And that's what I'm going to do here so you can see how the units work out. So for our E cell, we've got 1.10 joules per coulomb. So our moles of electrons cancel, our coulombs cancel, and we're left with units of joules for our delta G, which is energy. So that's good. All of our units work out. So our Gibbs free energy that we get for this reaction comes out to being negative 2.12 times 10 to the 5th joules, and I often will convert it into kilojoules because joules are such a small unit of energy, so that's negative 212 kilojoules. And so just as we expected, we got a negative value for our delta G, which tells us the reaction is spontaneous. Okay, let's try one more example where we calculate the free energy change. We have aluminum plus chromium 3 plus ions becoming aluminum 3 plus ions and solid chromium. The standard cell potential is 0.92 volts. And so we have aluminum going to aluminum 3 plus. That is being oxidized as it goes from a 0 oxidation state to a +3 oxidation state. And we have chromium 3 plus going to solid chromium. So that chromium is going from a +3 oxidation state down to a 0 oxidation state. So the chromium is being reduced. And just like in our last example, notice that between chromium 3 plus and aluminum 3 plus, the charges are the same. So that means aluminum had to have lost 3 electrons when it became aluminum 3 plus. And chromium had to have gained 3 electrons when it went from chromium 3 plus down to chromium. So we don't have to write out the half reactions. We can see, since the charges are the same, that N is going to equal 3 moles of electrons in this example. So that's how many electrons are transferred between the oxidation and reduction half reactions. And our E cell is 0.92 volts, which means that's 0.92 joules per coulomb. That's the same thing. A volt is equal to a joule per coulomb based upon how the volt was defined. And so our equation that relates Gibbs free energy and standard cell potential is delta G equals negative N F E. And we're going to plug in negative 3 and then moles of electrons that were transferred in this case, times our Faraday constant, 96,500 coulombs per mole of electrons transferred, times our E cell, which is 0.92 joules per coulomb. You always want to check to make sure your units cancel properly, your moles of electrons, your coulombs cancel. You're left with joules, which is the units for energy. And for this problem, we get a Gibbs free energy of negative 2.66 times 10 to the 5th joules, or in other words, negative 266 kilojoules. And so, as we would have expected, we got a negative value for our delta G. We had a positive value for our E cell, and so both of those together tell us we have a spontaneous reaction. Up until now, when we've been calculating our cell potential, we've been calculating the standard cell potential. So cell potential under those standard state conditions only. 25 C, 1 molar solutes, 1 atm of pressure for gases. Now we're going to learn something called the Nernst equation, which will actually allow us to calculate cell potential under non-standard state conditions. So we could vary the temperature, or we could vary the composition of the reaction mixture. And notice when we see E cell, now it's written without that naught symbol. It doesn't have that little superscript 0 because it's telling us, hey, you're not under standard state conditions. Whenever you see that little superscript naught, that in chemistry means the standard state. So the Nernst equation is only used when we're dealing with non-standard state conditions. And you'll notice there's kind of two forms of the equation. They both are identical in terms of when you do the calculation, but some textbooks write it a little bit differently. So how this is read is your E without the naught is going to be your cell potential that you're calculating under non-standard state conditions, is equal to E naught, the cell potential under standard state conditions, minus RT over NF times the ln of Q, which remember Q is the reaction quotient. So reaction quotient saying we are having just any reaction mixture. Now, sometimes textbooks will convert that equation to the one you see below that, where you have E equal to E naught minus 2.303 times RT over NF, and now notice it's log of Q. So we went from ln of Q to log of Q. That 2.303 is a ratio when you're converting the ln to the log. So either one of those equations, depending upon what one you want to use, they will get you the same answer for E cell under non-standard state conditions. I just wanted to point that out in case you come across both of them in different contexts. They are the same thing. So just a reminder, E naught is our standard cell potential in volts. R is called the gas law constant, and the value for R we're going to want to use here is 8.314 joules per Kelvin times mole. The temperature is T, capital T, and that has to be in units of Kelvin. F is our Faraday constant, 96,500 coulombs per mole. And N is the number of moles of electrons, so units of moles. So we've seen these before, so now we just have to apply it in order to calculate our E cell under non-standard state conditions. So by calculating that reaction quotient like we've done before. One other way that you might see the Nernst equation is the red equation written below. And this is an even more simplified version of the equation if the reaction is ran at 298 Kelvin, which is 25 degrees Celsius. So what they did when they wrote this version of the equation is they took everything that was a constant and plugged it in to get a number. So 2.303 times R is a constant. If you're at 298 Kelvin, that temperature would remain the same. And then F, Faraday's constant, is a constant. So all of those terms essentially come together to give us that 0.0592 volts that you see on the top. The N isn't included because the number of moles of electrons transferred will change depending upon the specific redox reaction. So this third equation is just yet another form of the Nernst equation that you'll come across. And this is a quick and easy one to use if your reaction is at specifically 298 Kelvin. So I will have all the equations for you on your equation sheet, and depending upon the problem that you're working on, you can choose what one that you're going to use. All right, so in this example of the Nernst equation, we're going to combine a lot of things that we've already talked about in this chapter. We have a galvanic cell given to us, and it's written in shorthand notation, so we got to interpret that. And we're going to have to calculate the cell potential. And notice how there are some concentrations in molarity and some pressures written after the species in that shorthand notation. Well, those are given to us because they're different. Some of them are different than our standard state conditions. So not everything is 1 molar. Not everything is at 1 atmosphere of pressure. So because of that, this is a Nernst equation problem where we're going to use that new formula. So we're going to calculate the cell potential at 25C under these non-standard state conditions. And since we are at 25 degrees Celsius, which is 298 Kelvin, we can use that shortened version of the equation that has already taken a lot of the constants into account. But first, let's take our shorthand notation and convert it into our two half reactions and calculate our standard cell potential first and foremost. So on the left-hand side, we have our anode, which is where oxidation occurs. And on our right-hand side, we have our cathode, which is where reduction occurs. And notice that our cathode, it's hydrogen. So that's actually the standard hydrogen electrode that zinc is being measured against. So the standard reduction potential for that cathode is going to be assigned at 0. So our oxidation half reaction then is going to be zinc going to zinc 2 plus 2 electrons. That's at our anode. And at our cathode, our reduction half reaction, and I'm just going to balance this, is going to be 2H plus, so 2 hydrogen ions, gaining 2 electrons to become H2 gas. And you would actually see that gas bubbling out. And so if you look at your standard reduction potential chart, we know that the standard reduction potential for the SHE, the standard hydrogen electrode, is 0 volts. And if we look up what the value is for the reduction potential for our zinc half reaction, we're going to see that it is negative 0.76 volts. So when we actually combine those and we calculate the standard cell potential, and we take our E cell of our species that's reduced and we subtract, or the standard reduction potential of our reduced species minus the reduction potential of our oxidized species, what we're going to end up with is 0 volts for the hydrogen half reaction minus negative 0.76 volts for the zinc half reaction, and that's going to give us a positive 0.76 volts for our standard cell potential. So we got a positive value so far. So that means if this reaction was ran at standard state conditions, we could for sure say it is spontaneous because the standard cell potential is positive. We don't know yet for sure if our non-standard state conditions is going to lead to a spontaneous reaction or not. That's what we're going to find out by continuing this. So next, what we want to do is take our two half reactions and add them together to write our overall equation. Now, when you add together half reactions, you don't want any electrons left in your overall equation. So in this case, we have 2 electrons as a reactant in the reduction half reaction, and we have 2 electrons as a product in the oxidation half reaction. Since they're both 2, they both have a coefficient of 2, they're going to cancel each other out. And our overall equation is going to be everything on the left-hand side of the arrows, so zinc plus 2H plus, and our products are going to be zinc 2 plus H2. So states of matter become important when we are going to calculate the reaction quotient, because remember with an equilibrium constant or a reaction quotient that you don't include pure solids or pure liquids. Essentially, they're assumed to have an activity of 1. So zinc is a pure solid, that won't appear. The hydrogen ion is aqueous, that will appear. Zinc 2 plus ion is aqueous, and hydrogen is a gas. So those other 3 species will appear in our reaction quotient calculation. So Q for this reaction is calculated just as if we would calculate the equilibrium constant. We have the products over the reactants raised to the coefficients from the balanced equation. So we're going to have the concentration of zinc times the concentration, or I should say partial pressure of hydrogen, over the concentration of our hydrogen ion. And notice the hydrogen ion has a 2 out in front of it, so we have to square that. Now we take our non-standard state concentrations and partial pressures and we plug them in to our reaction quotient calculation to actually get a value for Q. So for zinc 2+, we were told at the very top that the concentration is 0.001 molar. And for hydrogen, we're going to plug in the partial pressure that was given. That's 0.1 atmosphere. And I'm not going to include units. I know it seems a little weird mixing molarities and atmospheres, but units aren't even written for reaction quotients or equilibrium constants anyways. Over our concentration for our hydrogen ion, which that one is 1 molar, and that would be squared. And so when we calculate Q, we should get a value, and that comes out to being 0.0001 for our value of the reaction quotient. Now that we've got that, we can actually use our Nernst equation now. We've done pretty much all the work. Now we can plug and chug into that equation that we've got everything. We figured out our oxidation half reaction, our reduction half reaction. We calculated the E cell. We got 0.67 volts there, and we calculated the value for our reaction quotient. So the equation that we're going to use is E, so cell potential at non-standard state conditions, is equal to E cell at standard state conditions, so that's written with a naught symbol, minus, we have 0.0592 volts over N, where N is the number of electrons transferred, times the log of Q, so the log of the reaction quotient. So let's plug everything in. Our standard cell potential was a positive 0.76 volts. That goes in for E naught, minus 0.0592 volts. Remember, that comes from a combination of the temperature, 298 Kelvin, R, the gas constant, and Faraday's constant. So rather than plugging those in each time, that same value would always occur. Okay, over N. Now in this reaction, what is N going to be? Our oxidation reaction had 2 electrons as a product, and our reduction half reaction had 2 electrons as a reactant. So 2 electrons were transferred in this case. So N is going to be 2 moles of electrons. And it's not going to look like our units actually work out for this one because of all the units that are tied up into that 0.0592. So don't worry about the units right now. And then times the log of our reaction quotient, which we calculated was 0.001. So plug that into your calculator and make sure that you are putting everything in with the correct parentheses and everything. And your E cell at non-standard state conditions should come out to being, it's also a positive value, positive 0.878 volts. So in this scenario, the standard cell potential was positive, so the reaction was spontaneous. And when we ran it at non-standard state conditions, the specific ones here, it also was still spontaneous, but that doesn't necessarily have to be the case. Okay, so we are going to do our last problem using our Nernst equation, and we have our shorthand cell notation. So just a reminder, on the left-hand side, we have our anode, which is where oxidation occurs. And on the right-hand side, we have our cathode, which is where reduction occurs. Now, what makes this non-standard state conditions is one specific thing in this case. Because we are at 25 degrees Celsius, and our nickel does have a concentration of 1 molar for the aqueous ion. So it's because this aluminum ion is at 0.1 molar that it would technically not fall under the standard cell potential. That's the indication that, hey, now we are calculating a non-standard cell potential and we're going to use the Nernst equation. So that's why when you look at that shorthand cell notation, if they're giving you partial pressures or they're giving you molarities, they're usually trying to tell you that they're probably not standard state conditions. So let's write out our oxidation and reduction half reactions to come up with our overall equation so we can calculate Q. Our oxidation half reaction is going to occur at our anode, and that's for aluminum. So we're going to have aluminum solid going to aqueous aluminum 3+ ions. And for that to occur, the aluminum must lose 3 electrons. And our reduction half reaction is that of nickel. So we're going to have aqueous nickel 2+ ions picking up 2 electrons being reduced to solid nickel. Now, this is another good example because I wanted to review with you guys what you have to do when your oxidation and reduction half reactions don't match in the number of electrons that are transferred. So in this case, what is our N going to be? What is our electrons transferred? We have to balance this equation before we can add it up. And you might remember what you do when you have a different number of electrons lost than gained is you make them the same. So I'm going to take my oxidation half reaction and multiply everything in there through by 2. I'm going to take my reduction half reaction and multiply everything through in there by 3. And so I'll rewrite these so we can see our oxidation half reaction balance would become 2Al solid going to 2 aluminum 3+ ions, those are aqueous, plus 6 electrons. And our balanced reduction half reaction would become 3 nickel 2+ ions plus 6 electrons, and our product would be 3 nickel solid. So now when we add together those two half reactions, we can cancel out our electrons, because remember, you never want to include electrons in an overall equation. They should always cancel. So that's the point of doing that step. And also that tells us our N as well. So N is going to be equal to 6 moles of electrons. That's how many electrons were transferred total. So those will cancel. And let's write our overall equation. We're going to have 2Al solid plus 3 aqueous nickel 2+ ions going to 2Al3+ aqueous aluminum ions plus 3 nickel, and that's solid. So your aluminum on the reactant side is a solid, your nickel on the product side is a solid. Neither of those are going to get included in your reaction quotient calculation. The only two things you need to worry about are your aqueous nickel ions and your aqueous aluminum ions when we calculate Q. The other thing we need to find is our standard cell potential. So we have our oxidation and our reduction half reactions. We're going to have to consult our standard reduction potential chart to calculate E cell. And so that's going to be equal to the reduction potential of our reduction half reaction at the cathode minus the reduction potential of our oxidation reaction at the anode. And so if we look up our reduction potential for our reduction of nickel, that should give us a negative 0.25 volts, and that's going to be minus our reduction potential for our aluminum, and on our chart that gives us a negative 1.66 volts. So our standard cell potential comes out to being a positive 1.41 volts. So we'll keep that around and box it in until we're ready for it. All right, next let's calculate Q. So the next thing we're going to need, our reaction quotient. So looking at our overall balanced equation, we're going to have our products over our reactants. Our product is the only one that's being included is the aluminum 3+ ions, and that's going to be squared over our reactant, our nickel 2+ ions, and those are going to be cubed, the concentration of those cubed. Don't forget to raise the concentration to the power of the coefficients from the balanced equation. So for aluminum, now we're going to plug in that concentration. We have from our shorthand cell notation 0.1 molar, that's squared, over our concentration of our nickel, which is 1 molar, and that would be cubed. And that gives us a reaction quotient, Q, of 0.01 in this scenario. And so now we have our N, we have our moles of electrons transferred, we have our standard cell potential, positive 1.41 volts, and we have our reaction quotient, 0.01. So we've done all the work, we're ready to use the Nernst equation now. And just a reminder, we're at 25 degrees Celsius again, so 298 Kelvin. So we're going to use that modified version of the Nernst equation just to make it a little bit easier. So we're going to use a little bit of different color here. We have our cell potential at non-standard state conditions is equal to E cell at standard state conditions minus 0.0592 volts over N, all times the log of the reaction quotient. So let's plug everything that we found in here. Our E cell was 1.41 volts minus 0.0592 volts over our N is 6 for this reaction, 6 moles of electrons transferred, times our log of our Q was 0.01 that we calculated for our reaction quotient. And so that ends up coming out to an E, a cell value for non-standard state conditions of 1.43 volts. And then we got a positive value there. So notice in this example the closeness between these two values, the standard cell voltage and the non-standard cell voltage. Well, that's because the nickel was at standard state conditions, 1 molar, and the aluminum was the only thing that was a little bit different. Even the temperature was considered standard state temperature because it was at 25 degrees Celsius. So that's why those values are so close in this case. They're both positive, so the reaction is spontaneous.